Welcome to Lecture 25C, and this is the last of this series in Lecture 25, entitled Physical Manifestation of Vector Equations. Now, this is an optional lecture. There's a fair amount of material provided in the notes, but it is more or less to give you sort of an understanding of how vector field equations basically are structured in terms of describing a particular physical problem. So the objective is more or less to gain familiarity with manipulating vector field equations for physical problems. And the concepts and visualization skills are modeling of a dynamic and static vector fields for Maxwell's equations and determining the type of symmetry and field properties. And so this is very relevant to your ECE 221S course that you'll be taking next term. As usual, the second slide is just a summary of the slides to follow, so we'll just move on. All right, so let's look a little bit more into symmetry, and gradually we'll get into actually solving problems. But symmetries can come in different forms. For example, planar symmetry, cylindrical symmetry, circle symmetry, periodic symmetry, toroidal symmetry, just to name a few. I mean, just by looking at the picture, you can essentially see that if you were to move in a certain direction, right, and you were to look at the object, you probably would see no changes taking place. So in effect, you have already established, in part, a symmetry in the problem. And so, like I said, there are many types of symmetries, but these are the ones that we're primarily interested in. So for a high degree of symmetry, and these are the problems that we're going to be looking at, the vector f will point in one particular direction in an appropriate coordinate system, right? So for instance, if we're dealing with cylindrical coordinates, we talk about a radial direction. And so the field could be pointing in the radial direction, or it could be pointing in the z direction, or it could be pointing in the theta hat direction, okay? So if you can find the right coordinate system, the field will only be pointing in the direction of one of the basis vectors, the direction of basis vector. Also, the vector's magnitude will be a function of a single coordinate variable. And so it only depends on r, or it only depends on theta, or z if you're dealing with cylindrical coordinates. If it's Cartesian, maybe it only depends on the direction x, in other words, the value of x. And so these are things you want to establish, and you do that by graphing the fields and realizing what the symmetry is, and from there it becomes straightforward in terms of doing the calculations, more or less. So let's go through some examples illustrating high degree of symmetry. I've basically just shown here 2D problems because the vector fields become unwieldy if we're starting to graph things in 3D. So let's look at the example on the far left. If you look here, you can see that the fields are basically all in the x direction, either positive or negative. And you can also see effectively that the magnitude is changing as a function of x. Also, when you look at this, you would realize that there appears to be a source. Why? Because fields are coming outwards from this particular line here along the y-axis. So in this case, just by observation, you could say that this field is in the x-hat direction and depends only in the x direction. So if you go in this direction, there's no y dependency. It's only in the x direction. So this is a problem in which there's a high degree of symmetry. All right, so if you read through that, we need only to solve for the x dependency of the vector field. And the vector field f is constant uniform for a fixed value of x and a varying value for y and z. So imagine this being a trace, right? And you were to move in the z direction, but hold the value of x fixed. If you move in this direction, the arrows are all the same length. No change in magnitude. If you're moving in the z direction, which would be outwards, right? If we made uniform, then moving in this direction, maintaining x fixed, these arrows' length would not change as well. So we know that effectively that for constant x, in y and z, the field remains uniform and always pointing in the x-hat direction. Here's an example of a rotational field. So in this case, basically, if you were to follow a circle, you would find that these lines all have the same magnitude. So effectively, what you can essentially say, that the field magnitude depends only on the radial position, where square root of x squared plus y squared is the radius. And the field basically is in the theta hat direction. And so this would be representing the theta hat direction. Here I've shown it in Cartesian, but we'll actually be solving this problem as if it was a problem in cylindrical coordinates. Recall from section 4.2 reading assignment 0 that theta hat is this. Okay, so you can either write it explicitly as theta hat right off the bat, or you can write it in this form. But we are going to typically be operating in such a way that we're working with a theta hat. And the last example would be, for instance, if the field is radial. If it's radial, again, if we were to draw a circle with constant radius, along that periphery, the field lines would all be pointing in the same direction, in the radial direction, and their magnitudes would be the same. So it'd be uniform on a given circle of radius r. And so this depends, magnitude that would depend only on the function r. Notice as you move outwards, the length of these arrows basically is changing, which means the magnitude is changing as a function of r. So this is what we mean by establishing the degree of symmetry, and these are examples of high degree of symmetry. So these examples you can find at this particular link if you wish to do so. Okay, so now we'll move into the example I had mentioned earlier in terms of looking at Maxwell's equations, in terms of how vector field equations are put together to describe a physical problem. So let's take simple moving towards more complicated. Consider the solution of a single vector field F starting with Helmholtz equation. Okay, so we know that the field can be described in terms of minus the gradient of a scalar potential plus the curl of a vector potential. And we've already shown how we can move through that to basically say that the curl of F is equal to J, and the divergence of the vector field F is equal to some rho, and typically J and rho are given. And so in principle, the problem can be solved. In other words, we can determine what the vector field F is as long as we understand the properties occurring at the boundary. All right, now we're going to look at a case where we have two time-dependent coupled vector fields. So for instance, one vector field we're going to call H, and it's a function of position, that's x, y, z, and a function of t. And another vector field D, we'll call it, x, y, z, and also function t. And the example is coming. I'm just telling you this is just another possibility. So the objective of the next few slides is to become familiar with the manipulation of coupled vector equations and then determine a strategy for obtaining a solution to the two fields under the following limiting conditions. Time independence, which means we're dealing with a static problem, and a problem in which a high degree of symmetry exists. So under these two conditions, we basically can apply Stokes' theorem or divergent theorem, depending on whether or not we're dealing with a source-free problem or an irrotational problem, to solve for the vector field F. If you want more information, you can go to sections 4.5 and 4.6 of Reading Assignment 4 for a more detailed discussion of this material, but it's beyond the scope of this course. The next few slides are quite dense. And so in these next slides, I'd like to sort of make the connection between a physical type of problem and how these problems are basically structured in terms of vector equations. So in particular, we're interested in the physical manifestation of vector equations in time-invariant electromagnetics application. And we'll start with a condition under which everything is time-variant and then evolve towards a situation we're dealing with a time-invariant problem. And this is a class of problem that we can basically deal with under certain conditions in this course and going forward. So we'll start basically just by writing Maxwell's equations under dynamic conditions. And these are basically coupled vector equations and involving four vectors, D, E, B, and H. But D's and E's and B's and H are typically interrelated with respect to each other. And in fact, the problem can be even more complicated in that they're all interrelated with each other. But we're going to keep it simple at this stage. So what I've drawn here basically is four basic sets of combinations that one can consider. And these are the laws governing electromagnetic fields for an isotropic material under time-varying conditions. Now, what does isotropic mean? Isotropic just means no matter in which direction you look at a material, the properties are the same. Okay, so it's not direction dependent. And so that makes the problem quite simple. It becomes a linear system. And so you might ask yourself, well, these laws, well, they're laws in a sense. Observations have shown them to basically be true, and we just have to take them at face value. But nevertheless, these laws are written in the language of vector calculus. So for instance, something called the electric field is equal to the minus of a gradient of a scalar potential minus partial derivative with respect to t of a vector potential. And the vector potential, the curl of it, is equal to a b. So these are sorts of things that are given. You don't question them. This is just the way it is. If we apply the curl operator on both sides of equation 1, it's a curl of E. Curl of grad phi is 0 because it's a conservative field. And you're left with minus d curl of A dt. But because of this relationship, this becomes curl of E equals minus dB by dt. So this is one of Maxwell's equations. This is actually Faraday's law. Okay, working with the fact that del cross A equals B, we can apply the divergence theorem on both sides, and we end up with that the divergence of B is equal to 0. So this is Gauss's law for magnetic flux densities. This is another one of Maxwell's equations. Notice that basically at this point we have a B, we have an E, but effectively two equations, but nothing involving divergence of E, just the B. So we need more equations. And so we do have another equation, which is a physical law. This is Ampere's law in vectorial form. The curl of the magnetic field H is equal to J, which we'll explain shortly. It's a form of current flux density. It's a function x, y, z, and t, plus dd by dt, d being displacement field. If we take the divergence of this on both sides, then we end up with basically equal to divergence of a curl is 0. And we end up with the divergence of JE plus divergence, the partial derivative of t with respect to divergence of d equals 0. Well, it turns out if we look over here, that we have another one of Maxwell's equations. This is Gauss's law for displacement fields. And so if we make use of this information, then we can also show that the divergence of J subscript E is minus d rho E dt. So this is sort of an outcome of doing divergence on this. But the basic Maxwell's equations will consist of this equation, this equation, this equation, and this equation. And this is sort of like a byproduct. However, this is important because when we're dealing with equations in which motion is concerned, we typically use this formulation. And so if you look here now, we have more or less everything is defined. E is an electric field, has certain units. D is displacement flux density, has certain units. Rho E is a charge density. H is a magnetic field. B is a magnetic flux density. And this JE, which I've shown above, is sigma E plus J con. This is a convection current. So this is motion of charge. This basically is Ohm's law in vectorial form, where sigma is basically electrical conductivity. So this is basically the motion of charge in response to electric field, and this is general motion of the object as a whole. All right, and you can have additional terms here, which I have not included, but more or less a lot of the physics is wrapped up in terms of how we describe the right-hand side here. But we're not going to go into it because effectively this is not a course on physics. I just want to show you specific relationships. In isotropic materials, we also have the relationship between B and H. You have basically just some scalar coefficient, which we call the magnetic permeability. And we have the displacement flux density equal epsilon times the electric field, E being called the dielectric permittivity. And this J convec was convective current flux density, which is just the motion of charge on its own. That's it. All right, so we're going to now look at these set of equations. We'll just sort of very briefly mention the time-varying case and figure out how do we go from the time-varying case to the static case. And so let's start with the time-varying case. E and H are a function of time and are unknown. JE and rho E are given. Two divergence equations and two curl equations need to be solved. So we have a curl with respect to E, and we have divergence D, but D can be represented in terms of E. So actually this just becomes a divergence in E and a curl of E. Alternatively, we can express E in terms of D, in which case this would be a curl of D here and a divergence of D here. Also, we have curl of H is really equation, and we have over here basically a divergence of B. So we have here something involving H, but H can be represented in terms of B. So we have curl of B and divergence of B. So we have essentially 4 equations, and we have an equation involving a divergence and a curl for both cases. So in principle, a solution is possible, but it's a more complicated problem to deal with because it's all coupled. Okay, note, JE can take on different forms depending on the type of problem. We just discussed this briefly when we discussed this term here. And so, as I said, this is best dealt with in a course that deals with the physics of the problem. All right, the problem that will be interesting is the static case for purpose of doing types of problems involving the divergence theorem and Stokes theorem. The static case, in the static case, E and H are independent of time and are unknown, but JE and rho E, both independent of time, are given explicitly. Okay, so JE is just given to you in some form or another. All right, so that's it. Difference is here, it's given explicitly. It's not coupled in any way. So we end up with 2 divergence equations and 2 curl equations that need to be solved, but we end up with decoupled equations. So we have a pair involving the divergence E and the curl of E, and another pair involving the divergence of H and the curl of H. They're independent of each other. And so those are problems that we can solve if we apply certain symmetry, at least in this course. Now, these are just details. I'm not going to go into any detail, but we have something called a gauge and condition, which is a constraint equation that we impose on A in order to obtain a unique solution. You'll notice up here, basically, we have a curl of A, but there's no mention of the divergence. And so if you want A to be unique, you basically have to specify its curl and its divergence. Anyway, it gets more complicated than that, but nevertheless, I'm just mentioning there's more to it than meets the eye. The details of the gauge imposed for the static case and time-varying case are described in section 4.5 of reading assignment 4. You're not responsible for any of this material in section 4.5, nor do you need to worry about gauges for this course. I just mention it here because it gives you some insight as to how involved this gets when you actually look at real physical problems. The second note is that the equation curl of E equals minus dV by D becomes the curl equals minus dV by dt plus the curl of V cross B if there's relative motion, where V is the velocity of relative motion. This second term that you see here is referred to as a motion-dependent term and governs the operation of an electric machine. By the way, this expression here is derived from first principles in one of the appendices, I believe Appendix D, in reading assignment 4, but again, you are just not responsible for material. You might want to look at this in future if you get into more details. Okay, so Maxwell's equations under static conditions, which means time invariant. And so in this case, we have decoupled vector equations. D and E are independent of B and H. So E equals minus grad phi, and the curl of E equals 0. In this case, we say E is a conservative field, or alternatively, since epsilon in our case is a constant, then we can also write D in terms of E, or the other way around. The curl of E equals the curl of D divided by epsilon. Epsilon being a constant, you can bring it outside, and you end up with this being 1 over epsilon curl of D, or you can essentially say that the curl of D equals 0. Again, D is also a conservative field. Let's look at B. The curl of A equals B, and the divergence of the curl of A equals 0. Therefore, the divergence of B is equal to 0. B is a source-free field. Or alternatively, since mu in our case is a constant, then the divergence of mu h being B, you can bring mu out because it's a constant, is equal to mu divergence h, and thus the divergence of B, right, basically can also be written as the divergence of h being 0. So h is a source-free field. Curl of H is JE XYZ. This looks like a current flux density. Mu in our case is a constant. Therefore, the curl of B over mu, where B over mu is equivalent to H, is 1 over mu curl of b. 1 of mu can come outside because it's a constant. And thus curl of b equals mu j of e. Divergence of j will be equal to 0 since d rho e dt equals 0. Divergence of d equals rho e. Epsilon in our case is a constant, therefore divergence of epsilon electric field, this e epsilon is d. E can come outside, so that's epsilon divergence e, and thus the divergence of e is 1 over epsilon rho naught e x, y, z. So this is sort of a manipulations you can do under specific conditions. Here we're dealing with a static case, which means no time dependency. Okay, so we're now nearing the end, and this is basically finally the types of equations we're going to work with. So the final vector equation set, these are decoupled vector equations under static conditions or time invariant. We'll have divergence of d equals rho e x, y, z, and the curl of d equals 0. So that's a conservative field. Or, if you want to write everything in terms of e, then the divergence of e is 1 over epsilon rho e, and the curl of e equals 0. Okay, so two different ways of writing it, given that d and e are related to each other. For h, we would have divergence of h equals 0, so it's a source-free field. Alternative, and the curl of h is j, e, x, y, z. Alternative, you want to express everything in terms of b, then the divergence of b equals 0, and the curl of b would be mu j, e. Also, divergence of j equals 0. So essentially, we'd have two source-free fields, b and je. So the generic vector equation set, here we go. We will use one generic field to represent d or e and h or b in the equations above. It'll be understood what f is in any particular context. For a conservative field f, we have equations divergence of f equals rho x, y, z, curl of f equals 0, where rho of x, y, z is either rho of e x, y, z or 1 over epsilon rho naught e x, y, z, depending on what we're interpreting f to be. For a source-free field f, we have the equations divergence f equals 0, curl of f equals j, where j is either j of e or mu j of e, depending on which field we're referring to. So this is a sort of a nice way of compressing everything down into something quite simple. And so we're either going to be handling this class of problems under high degree of symmetry, or be handling this problem under high degree of symmetry. So that concludes lecture 25C, and as I stated, this is not mandatory. This is just to give you a little bit of additional information to see how vector fields, mathematics, and physical problems are interrelated. Thank you for listening.